Good morning, everyone. We're the Building Airflow Enhancement Model Team. I am Joe. This is Curtis, Mac, and Brandon. Our project sponsor is Abboud Manufacturing Corporation, and our advisor for this project was Dr. Risi. Now, imagine having to work in a hot factory with little airflow every day for 40 hours a week. It's certainly not ideal. So, Abboud is a suit manufacturer who operates out of an old sewing mill in New Bedford. Their building is roughly 500,000 square feet. For the entire length of this, it's massive. It's over 100 years old and relies solely on natural ventilation to cool the building. Workers or management maintains, they try to maintain the temperature by opening exhaust fans, intake fans, but really does little to decrease the overall temperature. Windows are opened by workers at their discretion to somewhat mitigate their problem. So here's the floor plan of the facility. The facility is broken down into two floors. The first floor being the pant shop, and then we have a large unused storage area. So we decided to break this project down to the highlighted parts, or outlined in red, that being the pant shop and then the right half of the second floor. So for the second floor scope, we decided to cut this pretty much in half. You notice this is the Eton system. We wanted to model the Eton system, the press line, the stitching room. These were the real problem areas where a lot of heat was generated. There wasn't a lot of airflow. So we really wanted to focus on these areas. You can see this system is a conveyor system, a lot of moving parts, a lot of steam presses in there, sewing machines. They generate a lot of heat, and with little airflow in tight spaces, that heat gets trapped in there. On the other side of the coin, we have the distribution center on the top left here, which it's very open. There's very few workers. And really just not in our project scope. And then same with the cutting room as well. Just many tables, not a lot of workers again, not a lot of airflow. It's much cooler compared to the other side of the facility where it gets very hot. So really just out of our project scope. We wanted to narrow this down for computational efficiency. Modeling this entire 500,000 square foot facility is just not feasible. So we decided to use COMSOL. It's a multi-physics software package that will be able to model the heat transfer and airflow through our facility. We were very familiar with it. We were comfortable with using it. And that's after looking at other software packages, we were comfortable using this. Now, when it came to modeling the facility itself, we wanted to come up with an idealized model. You can see in this picture right here, it's very cluttered. There's a lot of moving parts. So it's just modeling this in its entirety in every detail is just not feasible. So we wanted to come up with an idealized model. And doing that, we turned these, you can see these rows of workstations right there and right there into rows in this geometry. And by doing that, the computational efficiency is much greater, and it's going to drastically decrease the computation time. And to go into more detail, Curtis is going to talk about those decisions.
Thanks, Joe. So prior to running our pant shop and second floor models, our team conducted some convergence testing to help better understand the parameters and the boundary conditions that are going to be used into our simulations. So this picture shown on the right is one of our test models that just includes an inlet window and an outlet window. And we ran these tests with both transient and steady state solutions. And that particular test is using a mesh setting of Finer on COMSOL. So we initially ran a heat transfer model in parallel with our airflow optimization models. And due to the reliance on natural convection, the best way to reduce the overall temperatures of the facility was through optimizing the airflow. So the only way, the lowest temperature in the building that it can possibly reach is the same as the outside temperature, so that's why we wanted to focus on optimizing the airflow. So our team really went for a divide and conquer approach to allow us to run more tests and more simulations on the facility. Although we did perform some preliminary work to develop a heat transfer model, we focused more of our time and our effort on the airflow, as it was the only way to really reduce the temperature in the facility. If you guys have any more questions regarding the heat transfer model, we'd be happy to answer them at the end of our presentation. So, as I stated earlier, we initially wanted to run our heat transfer and airflow model in parallel. So in early March, we went to the facility to collect our boundary conditions. So we got like fan speeds, window inlet velocities, machine temperatures, and ambient air temperatures. And we took all this data and we put it to compile a benchmark simulation. So what we have shown here is a velocity distribution of the pan shop. It's a 4-hour solution with intervals every half hour. And you might be able to notice that it reaches steady state really quick at about an hour. So for these reasons and due to our need for computational efficiency, we pursued steady state solutions. So in order to quantify our results, we analyzed the airflow, analyzed the total airflow rate that was traveling through these two planes. So the idea was to increase the amount of airflow in both the north-south direction as well as the east-to-west direction, which is why we created these two planes at these locations. The current state of the pan shop has decent flow traveling through the horizontal plane, but for our solutions, we really want to see increased airflow, and especially in the vertical plane. So to go into our pan shop solutions, I'm going to hand it off to Mark.
Thank you, Curtis. So here are results for the multiple simulations that we ran. On the bottom here, you can notice the benchmark March conditions one that we used initially. Joseph Abboud expressed a desire to know the best possible solution and the most practical solution. So up here listed are 9,000 cubic feet per minute fans that were used all throughout the whole factory. And from our research, that's what the basic rated fans were. As you can see through the results, the airflow is increased, and excuse me. And through that, it just wouldn't be comfortable for the workers, and the fans would also be very loud. So we found a more optimized result that's more practical by installing exhaust fans in the south side of the pan shop, and that just caused more comfort with a lower speed fan, and that's going to be shown on the next slide here. So on the left, these two planes are actually of the pan shop of the 3D model taken at 4 feet. They're of the velocity planes. So you can see through the March conditions shown earlier that a lot of blue, meaning a lot less airflow. And then here on the right is our optimized one. This has south exhaust fans here and intake fans on the west side and exhaust fans on the east. And through the vertical plane, it caused a 91% increase in airflow, and through the horizontal plane, a 79% increase. And to talk about the planes and how we quantified the second floor of the factory, I'm going to hand it off to Brandon.
Thank you, Matt. So here are the idealized geometry for the second floor, and the red lines represent the planes that would measure the flow rate going through them. And the biggest problem areas for the second floor were the press line and the heat-on system area, which are here in the northern area. And we wanted to follow the same procedure as we did with the pan shop, where we would quantify the flow rate going through these planes of our simulations and find the most optimal compared to our benchmark conditions. And all throughout the ceiling of the second floor is a sawtooth roofing. It has exhaust fans installed, and it has a very complicated geometrical feature that if we were to model it in COMSOL, it would be increasing the computation time by a lot. So we look to idealize this model, idealize this geometry into a flat ceiling with a constant flow rate going through it, where that flow rate was based on a calculated flow rate of the exhaust fans themselves. And so we ran 4 simulations. 2 of them had 2,000 CFM fans, and the other 2 had 3,000 CFM fans. And for both the 2,000 and the 3,000 CFM fans, we had outlet and an inlet for the sawtooth. And for all 4 simulations, all windows were open. On the left is it's a slice of the velocity distribution of the second floor for the benchmark March conditions. The slice was taken at 5 feet because the people that are in these problem areas are going to be standing. So as you can see, it's very minimal flow rate. And for our optimized conditions, we had the 3,000 CFM fan with the inlet in the sawtooth area. And the 3,000 CFM fans are going to be very high up. They're about 13 feet up in the air. And knowing that, we can then proceed to understand that the flow rate that is going to be felt by these workers is very minimal, and that creates the best possible and the most practical solution. And as for the percent increase from the March conditions to the optimized conditions, we had a 509% increase in the north plane and a 656% increase in the south plane, and a 689% increase in the west plane. And now to talk about the future work in this project, I'm going to hand it back off to Mac.
What future groups or people need to do is assess the accuracy and the convergence of these models with heat transfer. Our initial results were promising, but these just need to have additional work to them, including the March conditions. That includes the temperatures outside as well. And also, with the heat transfer models, the airflows that we found need to be simulated with heat transfer and then quantified to see how those actually bring down the temperatures themselves. So as for a cost and budget, we had an initial budget of $1,000, and the only cost we had throughout the year was for our senior design poster. So we came in under budget at $825. So listed here is our timeline. So for our first semester, we focused mainly on data collection inside the factory, modeling the factory itself, getting the boundary conditions that we're going to use for our simulations. And then as for the second semester, what we really did was focus on the simulations that we need to run for the pan shop and the second floor for the airflows, as well as running our heat transfer model for the pan shop in parallel. Does anyone have any questions?